This is the great thing. So it actually started with, I always put it in this phrase, it was a dopey idea in my brain. And it really was, at that point, unstructured, right? You had these different ideas of how you could do things. There were some crude sketches. Back then, I had the ability to work with a group of engineers. These are graduate level engineering students at the University of Minnesota. And this was one of the projects. So that was the fun part of this, is to get some very bright people who understood electrical engineering and mechanical engineering and medical devices. So you bring the interest of those kind of areas, right? Because you knew that this is an electrical engineering problem, it's a mechanical engineering problem, and then you needed to make it so that it fulfills some of the requirements of a medical device. So the engineers were pulled together. I was their sponsor, and we were developing this, coming up with some of the crude embodiments. From that, we were able to reduce it into a patent. And so that patent was the first part of this. One of the engineers went on to become an employee of the company. So that was one of the outputs, that this was of an interest enough to him. We were certainly very happy to have him join. So as the idea was forming, the company was forming, and then this was the convergence where this specific individual said, I'd like to be involved in this in a more significant way. So that individual, Kinjo Sham is his name, he was also instrumental in helping design some of the specific embodiments. Like, what did the brace look like? What did the circuitry look like? What was the actual pulsed electromagnetic field? So between him and I, we figured out what those parameters were, right? What do we think would really work in terms of stimulating the cells? Because in many ways, it's a specific amount of pulsed electromagnetic frequency, right? That's the F. That frequency is also important. Is what's the lock and key? What's the right frequency to stimulate these cells? Because all cells are different, and they'll be stimulated at different frequencies, right? So in many ways, it was research, and I would say trial and error, when we're doing stuff at the cellular level. So he was a big part of this. And then obviously what you need to get this going is investors. So as we were developing this, I was involved in going out and raising capital for this. And then you start thinking about what I said in the beginning. What is your regulatory pathway? And what is this something that you need to go through the FDA or not? And a lot of that depends on the claims. What are you going to claim this device does for people? So we had consultants to come in to help develop that. And to me, that's probably the most exciting part of this. Because whatever idea you have, you're starting to refine it with all of these inputs to kind of hopefully lay it up for the most successful path. How do we consolidate the heat and electromagnetic therapy in one pod? And we were calling it a pod at that time. That was tricky to kind of bring those two therapies. And how are we going to turn on the electromagnetic therapy, right? Because you want it to have an effect as you kind of slid it into the brace. So that engineering challenge of turning it on and combining two different, if you will, sensory functions, a magnetic field and a heat, kind of coalescing those two was not an easy engineering challenge, right? And the other one that I think all medical device companies are challenged with is cost of goods, right? Because you need to make this and design it at a price point that you can still afford to manufacture it at scale, so you could sell it at a competitive price. The trick is, and we learned this at OrthoCor, the trick is not how do you design it for one use. How do you design it that you can manufacture tens and thousands? So a lot of times, what medical device engineers realize is you have to incorporate what's called design for manufacturability early on. So when you're designing something, you're thinking about its performance, its tolerance, what is it intended to do? And you're thinking about a product. We came across early on, Well, we're not going to make one product. We want to manufacture tens and thousands, right? So how do you implement all the regimens, which is called design for manufacturability, so that your costs are low and you could have reliable, reproducible manufacturing processes? That was not easy to do. But I give tremendous credit to the engineering team, led by Gill, that he was able to unpack a lot of those problems. So at the cellular level, you think about the pulsed field. The pulse field, as I said, is going to perturb the membrane. And in this case, we're looking at the membrane of the cells that lays down the cartilage. It's going to lay down the cartilage. Those cells then, as you provide the right frequency, remember there's a lock and key, if you provide the right frequency, the idea is that you're going to then stimulate those cells to lay down the proteins that they're designed to make. So for example, the cells that are in the joint of your knee that lay down cartilage, they're going to make the collagen that is the constituency of what makes up cartilage. They're not going to make the protein that resembles the hair follicle, right? So these cells are already pre-programmed. They know what their job is. So if you can stimulate them to put down more protein, that's a good thing. And then on top of it, if you can bring more blood flow to the area, they're giving that nutritive supply, that nutritive signal to do more of what they're being asked to do. So that's the thinking. The challenge is it's very difficult to kind of measure this, from how thick was your cartilage before and after, because it's a very thin, if you will, area of cartilage. It's difficult to measure that. So you're left with attempting to measure it functionally. Does the person feel better, right? Is the pain relief appreciated? Is the person's quality of life improved? And you have to ask them to take some questionnaires to respond to that. Is their range of motion improved, right? Are they able to move it, the joint, in this case the knee, at a different level where they couldn't have done it before? So that's where clinical research comes in. You have to put the brace into the hands of people that are suffering, in this case with arthritis of the knee. You kind of get a baseline of what you believe is their baseline pain, quality of life, range of motion. Then you put the brace on, and then you continue to measure them over a period of time. All right? And then if you want the real rigor, because you always worry about placebo, right? Do they just want to get better? So the right way to approach that would be to do a placebo, where you put the brace on, but you don't turn on the gas, right? You don't put anything that has electromagnetic field stimulation, right? And that's a way to think about really the focused, specific impact of whatever therapy you're trying to deliver.